everyone. First of all, I would like to thank the organizers, particularly Professor Patnaik, for his kind invitation. I truly appreciate this opportunity to showcase our research findings at QMAT 2026, and that is the title of my talk. And I'm from this Institute of Nanoscience and Technology, which is based in Mohali, and this happens to be the first and the only institute in India which has been established by the Government of India for the pursuit of research primarily in nanoscience and technology. This is the official mandate that we need to adhere to. It is located only 250 kilometers from here, and at INST we pursue research on diverse topics cutting across multiple disciplines, primarily in these three units, in these three research domains, and I belong to the quantum materials and devices unit. And I need to acknowledge my group of PhD scholars, both past as well as present, because today I'll be presenting the work done exclusively with my PhD scholars. And I'm into scientific computing, therefore the supercomputing resources provided by CDAC Pune under the National Supercomputing Mission and the in-house supercomputing facility of INST, that also I would like to acknowledge gratefully. And our students register for their PhD at the neighboring institute, IISER Mohali. So now, broadly speaking, we pursue research on two-dimensional materials for different kinds of energy conversion, such as piezoelectricity, photovoltaics, photocatalysis, and next generation electronics based on the charge, spin, and the Valley degrees of freedom. And apart from using the plane wave density functional theory based approaches, we also build models from the scratch and implement them via coding. Particularly in these works, we have done that. And in this talk, I'll be primarily concerned with the consequences of the breaking of inversion symmetry together with the concurrence of spin orbit coupling in two-dimensional materials, which leads to the emergence of several novel properties that can be gainfully exploited in the next generation electronics, such as flexible piezo-spintronic devices. So, now with the continued trend in the miniaturization of devices, the transistor density or the number of transistors in a device that has been rising exponentially with the passage of time, and as that continues, the channel length in the transistors, they are getting shorter and shorter with the passage of time, and we are gradually reaching the ultimate limit or the fundamental limit. The channel lengths in the transistors, they are reaching their fundamental limit or the ultimate limit, and at this stage the integration of 2D semiconductors into the channel is being actively pursued for the further improvement in the device functionality. So this is one aspect. The other aspect is this: humongous amount of data and information is being generated on a daily basis on social media platform, cloud platform, and so on. So there is a strong need for this data management, data storage and processing. And these degrees of freedom which arise in two-dimensional materials, they can potentially cater to the ever increasing need for data management, for data storage and processing. And if you reconcile these two aspects, the next generation channel semiconductor would demand a seamless merger of all these three properties. That is, the channel semiconductor needs to have a strong spin orbit coupling or a high Rashba constant, and a high out of plane piezoelectric coefficient, so that the external gate voltage source can be replaced by the intrinsic piezo potential under the application of external pressure or strain. And low dimensional materials or two-dimensional materials are by default flexible and stretchable. By default, they meet this criterion. So in summary, the next generation channel semiconductors, they need to be multifunctional. So that is the motivation behind our working on multifunctional two-dimensional semiconductors. Now, novel properties arise at the nanoscale which are usually non-existent in the bulk form of these materials. We can use the most widely studied 2D semiconductor, namely molybdenum disulfide, as an example to understand that this the bulk molybdenum disulfide comprises a multi-layered van der Waals solid. And when it is thinned down to the level of a monolayer, several interesting properties arise. Say, when you are going from bulk MOS2 to single layer MOS2, the point group symmetry changes from D6H to D3H, the symmetry is lowered, the inversion symmetry is broken, for which piezoelectricity arises in single layer MOS2, and on top of that spin orbit coupling simultaneously occurs in single layer MOS2, and that leads to the emergence of valleytronics. This is a property which also emerges in single layer MOS2. I'll talk about this property slightly later in my talk. And piezoelectricity in two-dimensional materials was first predicted theoretically in this JPCL paper sometime in 2012, and then in a few years down the lane it was observed and confirmed experimentally in these two articles. And in piezoelectricity, the word piezo, it's a Greek word, it's derived from the Greek word piezo, which means pressure. So it is the generation of electricity upon the application of pressure. And not all materials exhibit piezoelectricity. Only those materials which are non-centrosymmetric, where the inversion symmetry is broken, those materials show piezoelectricity. Graphene being centrosymmetric, it doesn't show piezoelectricity. But these two-dimensional monolayers, where the inversion symmetry is broken, they exhibit piezoelectricity. So as we can view in this video, that in the absence of strain or pressure, there is no polarization present in the system. As strain or pressure is applied along the armchair direction or the y direction, polarization is induced along the y direction. So piezoelectricity is about the polarization which is induced per unit strain, per unit uniaxial strain. So, and how do we quantitate piezoelectricity in a material? So these are the figure of merit for piezoelectricity in a material. The piezoelectricity in a material is quantitated by the piezoelectric stress and the strain coefficients, which we calculate, which we have calculated using these two approaches. So this is the piezoelectric stress coefficient. So this arises from the variation in the polarization per unit uniaxial strain. So this is the piezoelectric stress coefficient, and the piezoelectric stress and the strain coefficients, they are linked to each other through the elastic stiffness constant, and this piezoelectric strain coefficients, they are experimentally measurable. So finally we compute the piezoelectric stress, piezoelectric strain coefficients, that is this tensor components we calculate. And if you pay attention to the first two rows under normal piezoelectricity, they represent the in-plane piezoelectricity, while the last row corresponds to the out-of-plane piezoelectricity. And this is the top view of single layer MOS2, which shows that the inversion symmetry is broken in the xy plane of this monolayer, for which it shows in-plane piezoelectricity, but the inversion symmetry is preserved along the z direction, for which it doesn't show any out-of-plane piezoelectricity or out-of-plane electric field. So how can you induce an out-of-plane piezoelectricity in this single layer MOS2? It is possible if you can turn this into the so-called Janus structure. So the word Janus is derived from the Roman god Janus, which has two different faces to it. So if here in this case, if you replace the top layer of sulfur by a layer of selenium, then you can turn this into the, you can convert this into the so-called Janus structure, and as you turn this into the Janus structure, the inversion symmetry is broken along the z direction, for which an out-of-plane piezoelectricity arises in these Janus structures. And also the formation of the Janus structure, that introduces an asymmetry in the crystal potential, as we can observe over here. This is the pristine MOS2 structure. Here the crystal potential is symmetric. As you turn it into the Janus structure, the crystal potential becomes asymmetric. The asymmetry in the crystal potential, that builds up an electric field along the z direction, and the out of plane electric field together with the spin orbit coupling, that brings about the Rashba effect, which can be gainfully exploited in spintronics, and that was the motivation behind this work. So the Janus structures were first studied theoretically, were first reported theoretically in this EPL paper in the year 2013, and spin orbit induced spin splittings in polar transition metal dichalcogenide monolayers, that was the motivation behind their work. And then in a few years down the lane, the Janus structures have been synthesized experimentally. I mean, in two different experiments. Here they started off with a single layer of MOS2, and here the top layer has been selenized. And in another experiment, they began independently with a layer of MOSE2. Here the top layer has been sulfurized. So, regardless of whether you start off with MOS2 or MOSE2, it is possible to generate or design Janus structures. So, the feasibility, so the experimental feasibility in the synthesis of Janus structures has motivated us, has prompted us to explore Janus structures in two-dimensional materials of different kinds of symmetry, right. So, before I present our work on Janus structures, I need to talk a bit about the spin-orbit coupling. Now, spin-orbit coupling normally naturally arises in a material containing one or more heavy elements. Then the spin-orbit coupling acts as a perturbation to the main Hamiltonian, and it brings about a Zeeman like spin splitting, a Zeeman type spin splitting, out of plane Zeeman type spin splitting, and heavier the element, higher is the Zeeman type spin splitting, higher is the spin-orbit coupling. Now, on top of that, if you apply an electric field along the z direction, the potential changes from this to that, and that introduces an additional term in the Hamiltonian. This is the Rashba Hamiltonian, and what it does is that it lifts the in-plane spin degeneracy in this parabolic bands. So, one parabola splits into two parabola. This is the energy splitting and the momentum offset, and this momentum dependent spin splitting is quantified by the Rashba constant. So, when higher the spin-orbit coupling, higher is the Rashba constant. And now this channel material needs to be a Rashba semiconductor in order to be able to control the flow of spin from the source to the drain. Okay? And then apart from the charge and the spin degrees of freedom of an electron, another degree of freedom, namely the Valley degrees of freedom, arises in single layer MOS2. So, this is the top view of single layer MOS2, which shows that the inversion symmetry is broken in the XY plane of this monolayer, for which it shows an in-plane piezoelectricity, and this is the band structure which has been calculated in the absence of spin-orbit coupling. And as you turn on the spin-orbit coupling, a Zeeman type spin splitting is found to occur at the K point in the band structure, and it gets a time reversed partner K prime or minus K. So, this is due to the breaking of the inversion symmetry. As the inversion symmetry is broken in the XY plane of this monolayer, so the opposite spins are found to be locked to this momentum values K and K prime. K and K prime or minus K, they can play the role of zeros and ones in electronics, and they can be used to encode information. So, apart from the charge and the spin degrees of freedom of an electron, another degree of freedom, namely the Valley degrees of freedom, arises in a single layer MOS2, and so this is how this is the emergence of Valleytronics in two-dimensional monolayers, and this single layer MOS2 happens to be the most widely studied 2D Valleytronic material. So, we have also contributed a bit in this direction, and we have also proposed two-dimensional monolayers beyond single layer MOS2, which shows properties complementary to that of single layer MOS2. Like here in HFN2, it shows a large Zeeman type Valley spin splitting at the conduction band, not at the valence band. And in the interest of time, I will be presenting only these two works of ours in this talk. And now this is a 7-layered structure which has been grown experimentally, where MON2 layer is sandwiched between two layers of silicon nitride. It does not have any bulk counterpart. Now, if you replace SiN2 layer by a layer of chalcogen atoms, so you can turn this into the so-called Janus structures, which have been widely studied, at least theoretically. So, now the top view reveals that the inversion symmetry is broken in the XY plane of this monolayer, while the side view shows that the inversion symmetry is broken along the z direction or along the out of plane direction. So, therefore, as a consequence of that, these Janus monolayers, they exhibit in-plane piezoelectricity as well as out-of-plane piezoelectricity as well, and the piezoelectric stress coefficients are found to be proportional to the electronegativity difference ratio. And also, the Janus monolayer, which contains the heaviest anion and the lightest cation, that Janus monolayer shows the highest piezoelectric coefficient out of all the Janus monolayers studied. So, what we conclude, what we understand here is that the piezoelectric stress coefficients are proportional to the anionic polarizability to the cationic polarizability, anionic radius to the cationic radius. Now, as the inversion symmetry is broken in the XY plane of this monolayer, in addition to exhibiting the in-plane piezoelectricity, it also shows Valley polarization. That is what we find. Opposite spins are locked to the momentum values K and K prime, and the extent of the Zeeman type Valley spin splitting is higher in the Janus monolayers containing the heavier elements. And since the inversion symmetry is also broken along the z direction, an out of plane electric field arises in it intrinsically, and that together with the spin orbit coupling brings about this momentum dependent spin splitting, or the Rashba spin splitting, which is quantified by this Rashba constant. So, it also shows a Rashba type spin splitting. And then we proceeded to find the appropriate descriptors for this Rashba constant, and the Rashba constant is found to be proportional to the difference in the electrostatic potential between the edges of these two-dimensional monolayers. Now, the negative gradient of this electrostatic potential that builds up an electric field along the z direction. So, higher the out of plane electric field, higher is the Rashba constant. That is what we find over here, and the Rashba constant is also found to be proportional to, it is also found to scale with the trace of the Born effective charges on the chalcogen atoms. The Born effective charges are not the static charges, these are the dynamical charges. So, if you displace an ion along the x direction, polarization can be induced along the x, y and the z direction. So, this is a tensor. So, the Rashba constant is also found to be proportional to the trace of the Born effective charges, and also the macroscopic static dielectric constant. Rashba constant scales inversely with the Bader charges on the chalcogen atom, the work function and the electronegativity difference. And so, if you can come across this 2D monolayers such as CDT or ZNT, these kind of monolayers which have a AB type polar buccal structure, there are several advantages. So, that this obviates the need for the formation of Janus structures. You do not need to design Janus structures, because due to this polar buccal structures, an out of plane electric field intrinsically arises in them, which together with the spin orbit coupling brings about this Rashba type spin splitting in the conduction band. And since cadmium is heavier than zinc, here the Rashba constant is higher. And also, since the inversion symmetry is broken along the z direction, it also shows out of plane piezoelectricity. And as the inversion symmetry is broken in the xy plane of this monolayer, it shows in plane piezoelectricity and also a valley polarization also, and the extent of the Zeeman type valley spin splitting is higher in cadmium telluride, because cadmium is heavier than zinc. So, these monolayers, the CDT monolayers also shows nonlinear valley Hall effects also. This is for the experts in the audience, and the same also applies to the MGTE monolayers, which are also stable. So, in summary, we find that these three monolayers, CDTE, MGTE and ZNTE, they are stable, they have a wide direct band gap and a strong spin orbit coupling, which shows up as a high Rashba constant, a reasonably high Rashba constant, or Rashba type spin splitting occurring at the conduction band. And so, since they exhibit a large Rashba constant, so therefore, they satisfy this condition. And also, these monolayers, they show a reasonably high out of plane piezoelectric coefficient. So, therefore, they also meet this criterion, they satisfy this condition, and these three monolayers, they show small Young's modulus. So, we understand that these monolayers are stretchable and flexible. So, this condition is also satisfied. So, therefore, we propose that these three monolayers would be suitable for flexible piezo spintronics. And now, this ferroelectricity, it is time to switch the gear to ferroelectricity. Now, ferroelectricity is a subset of piezoelectricity, and ferroelectric materials, they show a spontaneous polarization, unlike the piezoelectric materials which exhibit polarization under the application of electric field, strain or pressure. And now, here in the ferroelectric materials, the spontaneous polarization can be switched by the application of the electric field. So, there are two stable states of polarization, P and minus P. So, by the application of electric field, one can switch the direction of polarization from plus P to minus P. So, this plus P and minus P, these are dual degenerate and stable polarization states in a ferroelectric material, which can be switched by the application of an electric field. And so, this plus P and minus P can play the role of zeros and ones in electronics, and they can be used to encode information. So, therefore, they can find useful applications in non-volatile memory devices. Now, in a single monolayer, if one has to switch from one P state to the other, one has to transcend a high barrier. The barrier is very high because it would involve atomic displacements and a structural reorganization within a single layer. And that is the reason if you have to switch the polarization direction from plus P to minus P, the barrier is high. Now, how can you get around this problem? How can you circumvent this? So if you switch to van der Waals bilayers, where you can slide one layer on top of the other, the barrier is relatively lower. The switching barrier is lower if you move to sliding ferroelectricity, and that was our motivation behind working on sliding ferroelectricity in these bilayers. These bilayers can be exfoliated from their bulk counterparts, which are van der Waals solids. And now they are isostructural with MOS2. They have nearly the same structure as that of MOS2, and in the AB stacking sequence, the polarization direction is along the plus Z direction, and as you slide one layer on top of the other, the polarization direction reverses itself from plus P to minus P. So this is the sliding ferroelectricity, and as you are sliding one layer on top of the other, you are going from AB stacking sequence to BA stacking sequence. So, and you pass through this centrosymmetric paraelectric phase, which shows instability in the optical phonon modes. That is what we have observed over here. And then we have ascertained the origin of this reversal in the polarization direction as we slide one layer on top of the other. So that arises from the relative electrostatic potential difference between the individual layers. In this AB stacking sequence, this is the difference in electrostatic potential, so for which the polarization acts from this to this is the direction of polarization, and as you switch to the BA stacking sequence, the polarization reverses itself. So the relative electrostatic potential between the individual layers, that reverses itself. So that is the origin of this reversal in the polarization in this bilayer system. And also, since the inversion symmetry is broken in the xy plane of these monolayers, they also show valley polarization, that is opposite spins are found to be locked to this momentum valleys k and k prime. And what we find is that in this AB stacking sequence, the top of the valence band comes from the bottom layer, and in the other stacking sequence, the top of the valence band comes from the top layer. So this is, so layer can be a degree of freedom in this bilayer. That is what we observe over here, and that is what we have calculated the Berry curvature, the spin Berry curvature, spin Hall conductivity, and the spin Nernst conductivity. All this we have reported in our article, and in summary, what we find is that in this stacking sequence, the valley Hall effect will take place, or the spin Hall effect will take place in this bottom layer, and in this one, the spin Hall effect would be occurring in this top layer. So one can realize a hole driven layer polarized spin Hall effect. And this is an interesting application of piezoelectricity which we have demonstrated in these two articles. So this piezoelectric substrate would generate surface acoustic waves which would induce a strain in this two-dimensional hexagonal honeycomb antiferromagnetic material which is supported on the piezoelectric substrate, and this strain which will be experienced by this 2D hexagonal honeycomb antiferromagnet, and that would generate pseudo gauge fields, and the pseudo gauge fields can drive then the magnons through this 2D hexagonal honeycomb antiferromagnetic material. So Shivam and Faizi, they have developed models from the scratch using the linear spin wave theory in conjunction with the semi-classical Boltzmann transport equation, and so these details are discussed in this article. And in the interest of time, how much time do I have? 1 minute. 1 minute. I think I am nearly done. So, and we do collaborate with experimentalists and provide them with a strong theoretical support on a wide array of topics, as you can see over here: magnetoresistance, then this is supercapacitor, HER, OER activity, and so on. And in the interest of time, I skip this, and I think with that I come to the end of my talk, and thank you for your kind attention. Thank you.
So thank you, Professor Shankar, for ending the talk on a philosophical note. So the session is open for questions.
So you talked about MOSES. So my question is like, I think MOSES, the disordered MOSES is easier to make, to synthesize. So how are you controlling the genus structure of
So that is really up to the experimentalists how to control it. I am a theoretician. I can give pointers to experimentalists. Yes, and if in MOSSE, if you can control the concentration of the vacancies, the concentration of selenium, that's easier. Then replacing totally the top layer of sulfur by selenium, that can be a bit non-trivial. But say MOS 25%, SE 75%, or the other way around, that could be easier actually, and that has also been studied.
So have you find any instability in DFT calculation for any?
No, it is found to be totally stable. From all different perspectives, we find it to be stable.
Other questions? If there is no more questions, then let us thank the speaker.
Thank you.